All right, this is going to be the answer key walkthrough video for tomorrow's test. I'm going to try to do this pretty quickly. As with any of these videos, if you only need to see whatever example it is, skip through it because this is probably going to take a minute. All right, I'm going to try to show all work and explain at the same time. I do have a calculator, so here we go. All right. Number one, it says in a bag of red and blue marbles, the probability of selecting a red marble from a bag is 0.37. Find the probability of selecting a blue marble. This is one of those where we have red and we have blue. There's two things in here, and it's telling you that red is this. So this is where we take 1 or 100% of what we have minus the probability of what we're giving or given. Throughout this thing, I'm not going to do the P with the parentheses. I'm just going to substitute in the numbers. But so all I'm going to do is 1, which is 100%, take away what they're given, which is the 0.37. And that's going to get you the probability of 0.63. That's fine. In fraction form, that would be 63 hundredths. It would also be 600, or not 600, 63%. Any of those will be acceptable. That's pretty much the first one. Number two, two is with A and B here. It says determine if each event is an independent or dependent event. You don't need to find the probability. You just need to tell me if it's independent or dependent. So A quarter lands heads up and a nickel lands tails up. What you have to think when determining what type of event you have is, does the first event affect the second event? All right. In this case, for A quarter does not affect what a nickel does. So this is independent. For B, a coach randomly selects 2 students to demonstrate a drill. The example that I kind of gave today in class for those that asked was, if I was the coach, and let's say I've got little Johnny in my classroom, right? If I was the coach and my first choice for this drill is picking little Johnny, so I pick him. Does me picking little Johnny affect who I can pick next? And you might say no, but the thing is, what if I want to pick little Johnny again? Can I do that? I can't because I've already picked him on the first time. All right. So by me choosing a student for this drill and then me going to choose another student, I can't pick the one I picked first. So this ends up being dependent. Dependent. Okay. Number 3, explain whether the event is mutually exclusive or not. So you have to explain. You're not finding probabilities here. You're again just explaining. So it says a magazine contains 12 pages. You open to a random page. The page number is 2 or 9. When thinking about this, can the page number 2 also be 9 at the same time? And the answer is no. So since this cannot happen, this is going to be mutually exclusive. And it's going to be mutually exclusive because page 2 cannot, I'm just going to put can't, also be page 9. Okay? So because these things cannot happen at the same time, it is mutually exclusive. Remember, this mutually exclusive, you would think if it is, then it can happen, but they're kind of opposites. They're kind of opposites on what is and what is not. So there you go. Next one, find the probability of selecting a yellow jelly bean. So we want a yellow jelly bean from a bag with 3 blue, 8 yellow, 7 red, and 2 green. So the total is going to be 3 plus 8, 9, 10, 11, and 7 is 18, 19, 20. So there's 20 total beans on this. There's only one event happening, and that one event is us picking a yellow jelly bean. So we want the probability of yellow, which there are 8 yellows, and there are 20 total jelly beans. So this is fine. Uh, it could be simplified by 4, so that would be 2/5. That would work. It could be 0.4, could be 40%. Okay, all of those are acceptable. Every one of them. All right. Let me fix this too real quick. Sorry, not much better. Number 5. Dana has 9 green chocolate candies, 19 red chocolate candies, 14 yellow chocolate candies in a bag. She randomly pulls a chocolate candy from the bag, eats it. That's going to affect something. And then she pulls out another candy. We want to know what's the probability that Dana selects a green candy and then a yellow candy. So the and then that I circled, that means we are going to be multiplying these. All right. So in order for us to pull out a yellow candy, we have to do a green candy first. So the probability of green that we have is going to be 9 out of, let me do this addition real quick. So 9 plus 19 red candies plus a 14 yellow candies. So I got 9 out of 42 for my green candy. And then the yellow candy. Now, the yellow candy is not affected by the green candy. So I'm going to put all my yellows on this one. So that'd be a 14. But because she is eating this, uh, the first candy or whatever it is, she's eating the green candy. That means that it's not going to be put back into this bag. So that's going to affect the total number of candies that she can choose. All right. That's what that means there. So what I'm going to do is take 9/42, and I'm putting all of this into a calculator as a fraction. So it's going to give me the simplified fraction version. So 9/42 times 14/41 says syntax error. Oh, fixed it. Forgot to put the time sign. There we go. Sweet. 3/41. Okay. Now on this one, because it's a weird fraction, I would like for you to keep it as fraction form, but if you want, it would be about 7.3% or 0.73. So something like that. But I had to round it. I don't like doing that. I would definitely do the fraction. That's just me. Number 6. So these checkers problems get kind of long. So I'm going to read them, but I'm going to keep kind of referencing back to them. In a game of checkers, and you have to read them carefully because I messed up today. In a game of checkers, there are 12 red game pieces, important, 12 black game pieces, important. Okay? Julia is setting up the board to begin with playing. Find the probability that the first 2 checkers she pulls from the box without replacing the first checker will both be black checkers. Okay? Now, it does say find a probability on this, but I think the question is intended for you to just explain this because I think we're finding the probability in another question. So explain if this is independent or dependent. So what's going to happen here is we're just explaining whether it is independent or dependent. So does our first black checker pull affect what can be pulled next? And I forgot to do this. Very important part here says without replacing the first checker. Okay, so since we are not replacing the first checker, that's going to affect what can happen next. So because we're not replacing it, this is going to be independent. Because I'm just going to put this, the first checker is not replaced. Keep it simple. And that's it. Okay. I do want to make sure. Okay. Yeah. So number 7 is a continuation of number 6. So 6 was asking you, is it independent or dependent? 7 is asking you to find the probability. So again, sorry, I screwed up my my highlights. I like to highlight the number part in these, so it shows up a little bit better on the answer key. So 7 is the same thing. Game of checkers. There are 12 red game pieces, 12 black game pieces, just like before. Julie is setting up the board to begin playing. Find the probability that the first 2 checkers she pulls from the box without replacing will both be black checkers. So this is going to be the probability of a black checker times the probability of a black checker after the first black checker. So there are 12 black checkers in this box, and there are 24 because there's equal amounts of red and black. So that is the probability before you pull the first black checker. Then we have to pull another one. So if you take one out without replacing it, your total number of black checkers goes down to 11. And it doesn't matter what color checkers you have, but if you pull one out, red or black, your total amount of all of the checkers will end up going down as well. So I'm going to take 12 24ths times 11 23rds. That gets me 11 46ths, which will give me about, if you want a percent, which again, fraction is preferred, but it will give me about 23.9%, 23.9%, or, 0.23913, something like that, okay? Number 8. By the way, I know that since I'm putting this in a calculator, the calculator is going to give me simplest terms. I'll take equivalent fractions, okay? Simplest terms is preferred, and calculators will do that for you, but I will take equivalent fractions, just so you are aware. In a game of checkers, there are 12 red game pieces and 12 black game pieces. Explain how to find the probability if a black checker is drawn. So black checker is drawn, replaced, and then a black checker is drawn. State the correct probability. So this is a combination of both. So what's going to happen here, the explanations, it's kind of on you. So explain how to find the probability if a black checker is drawn. So, all right, I'm going to wing it here. What I would do is I would say find the probability. I'm going to abbreviate that because this is going to be a little lengthy. Find the probability of the first black checker then multiply that by the probability of the second black checker, which seems pretty straightforward. The one thing that I'd like to put is, I'm going to say after it has been replaced. My handwriting's not fantastic. I apologize, but I hope you can kind of see what we're doing here. So you're going to find the probability of the first black checker. Then you're going to multiply that by the probability of the second black checker after it has been replaced, which looks like this. There is 12 black checkers out of 24. That's your first probability of the black checker. Then what happens is you pull it out, see that it's a black checker. Replace it means put it back in. So you have the exact same probability as before. So this is different than the previous question, because the previous question, we were not replacing these black checkers, okay? So when you do this math, you're going to take 12 24ths times 12 24ths. And I know 12 over 24 is a half, so a half times a half is going to be a fourth, or 25%. So 1/4 or 25%. Okay, I believe that's the first page. All right, second page. Okay, so 2 socks are drawn from a drawer which contains there's 2 red socks, 1 blue sock, 3 black socks, and 4 green socks. Once a sock is selected, it's not replaced, so the probability of each, it's not replaced. So this is going to be, these are dependent then, in that case. A red sock and a black sock, so the probability of a red sock, you have 2 red socks out of, what was our total? 2, 3, 6, and 4 makes 10, so there's 10 total. Okay, so 2 red socks out of 10 total socks times how many black socks? We have 3 black socks. Since this is not being replaced, this is dependent, so your total socks will go down for that second draw. Okay, so we have 2/10 times 3/9, and I'm going to just leave these in fractions. We're going to move a bit quicker if I do that instead of keep switching to the conversion. So this will just be 1/15. 2 green socks, so we have 4 green socks out of the 10. Right? If we take out a green sock, leave it out, and then pull another one, our total green socks goes to 3, but our total overall socks goes to 9. Okay, so just like the one above it, so 4/10 times 3/9. That gets me a probability of 2/15. That looks like a Z. 2/15. Okay, that's 9 and 10. Next one, we have 5 quarters, 2 dimes, 13 pennies. Once a coin is drawn from a bag, it is replaced. So that'll affect the second, or that will not affect the second probability. I'm sorry. 2 coins are drawn at random, find the probability. So we have how many quarters? 5 quarters out of, let's see, 5, 6, 7, and 13 makes 20 total. 5 quarters out of the 20 total. That's for the first quarter. Then you draw it, see that it's a quarter, and put it back in because it's replaced. So then if you want to do the quarter again, the same amount of quarters are there and the same amount of coins are in there as well. So I'm going to take 5/20ths times 5/20ths. That's going to get me a probability of 1/16. 1/16. Okay. Scoot that over. Right. A dime and then a penny. So dimes, we've got 2 dimes over 20 total coins. Again, these are being replaced. So we would take our dime out, see that it is a dime, and then put it back in the bag. So the pennies that we have, there's 13 of them. And again, there's still 20 coins because we replaced this. So this is 2/20ths times 13/20ths. Yikes. So the probability of this happening is 13/200ths. 1, 10. Yep, that's right. Okay. So there you go. There's the probabilities. Number 13, at Plenty O Ice Cream Shop, there are 2 types of ice cream cones. Let me write this. 2 types of ice cream cones, 8 flavors of homemade ice cream, and 6 toppings. How many different choices do you have? If we are looking for the total choices, what you want to use is the fundamental counting principle. So you're going to take the ice cream types times the flavors times the toppings. So I'll write that on here. So we're going to take ice cream types. This is the fundamental counting principle, or the multiplication counting principle, or just the counting principle. So ice cream types times the flavors times the toppings. And that will get you your total number of outcomes. So we have 2 ice cream types times the 8 flavors times the 6 toppings. So 2 times 8 times 6. There's 96 of them. 96 different choices. Put equal sign. 96 different choices. Okay. Fundamental counting principle. 14. Diana separates. Interesting. I remember this question. I got it today. Diana separates her Skittles from her M&Ms. Sorry, I need some water. For each type of candy, she has 9 red candies, 4 green candies, and 7 yellow candies, 5 orange candies. So how I would interpret this, well, let's see the question first. So it says, are the events of drawing a red Skittle and an orange M&M dependent or independent? We want a red Skittle and an orange M&M. So what I circled after Diana, where it says separates, basically she has all of these M&Ms and Skittles mixed together, but she separated them out into 2 piles. Okay. If you choose, here's how we're determining this. If you choose a red Skittle, will that affect what you can choose from the M&Ms? The answer to that question is no. So this is going to be independent. Okay. Independent because the Skittle being chosen does not affect the I don't know how to draw that and sign. So I'm just going to put the M&M being chosen. Okay. So then it says it wants us to find the probability of the event. So it tells us that she's got equal amounts of these things. So you see, it says for each type of candy. So the Skittles probability is going to be, it's red, so we've got 9 red out of, let's see, 9, 10, 11, 12, 13. 13 and 7 is 20 plus 5 is 25. So there's 25 total. 25 total. Okay. So we have 9 out of 25. And since this is independent, the other pile is not affected. And I know it seems like it's coming from the same pile, but it's not. So the other one is not being affected because they're separated. So how many orange M&Ms? 5 orange candies. So be that. We got 9 25ths times 5 25ths. That gets me 9 over 125. So I'm just going to leave it like that. 9 over 125. Okay. I want to do it. So it's going to be 7.2%. It's actually exact. So that's why I put that on there. Okay. It's 7.2%. So not a great probability. All right, 15. Actually, I think this is it, maybe. From the tree diagram, ice cream options are shown in the table. How many possible outcomes are vanilla? So what I'm going to do is, since we already have the tree diagram, I'm just going to look to see where it says vanilla. Okay. So from the cone to vanilla, That's going to be everything after vanilla is going to be included. So those three would be included in this, right? Um, but then we have underneath the cone, we have the cup. And the cup, you can still get vanilla ice cream. And similar to the one above, it also has um, those three outcomes. So we have 1, 2, 3 vanilla outcomes with the cone, and 4, 5, 6 vanilla outcomes with the cup. So from the tree diagram, how many possible outcomes are vanilla? 6 possible outcomes. Oops. Outcomes are vanilla. Now there was actually supposed to be another tree diagram underneath this, but because I took and put this all on one page, I deleted it. So I'm going to actually erase these guys because I'm going to use them to answer the next question. So it says, what is the probability of you, so let me separate this. What is the probability of you selecting cup, chocolate, and sprinkles, and your friend selecting cone, vanilla, and nuts? So it says, and your friend. So there's two events here. There's your choice, and then there is your friend's choice. Those are the two events. Okay? So I'm going to do the probability on this, and then I'll check it with the tree diagram. So it says you want a cup, a chocolate, and sprinkles. Actually, I guess I'm going to use the tree diagram. It's here. I might as well. So a cup to chocolate to sprinkles. That's you. There's no other way. There's nothing above. So a cone is not, because a cone is not a cup. So there's nothing else that we need to worry about there. But there is only one probability out of a total of 12 where you are going to select the cup with chocolate ice cream and sprinkles. Okay? So we want you to choose and your friend to choose. If we want and, that means we're going to be multiplying these probabilities. Okay? So I'm going to erase this. Your friend selects a cone with vanilla ice cream and nuts. All right? So cone with vanilla ice cream and nuts. There's no other combination within this tree diagram where that is possible. Because again, everything below now is gone because it's not a cup. Your friend doesn't want a cup. So we have also 1/12 there that we're going to multiply by. One other thing that I kind of want to bring up is notice that like our denominators are the same. These are independent events, okay? And it doesn't ask, but these are independent events. And the reason that these are independent events is because what you choose does not affect what your friend can choose. Think about if you've ever gotten ice cream before. If you want a chocolate ice cream cone and your parents also want a chocolate ice cream cone, they can still get theirs even though you got yours, you know. So just kind of a situation like that, unless of course the ice cream place runs out of ice cream, in which case it is a sad day. But the probability then, and I'll point this down here, um, the probability of you exactly selecting a cup with chocolate with sprinkles and your friend selecting a cone, vanilla, and nuts, that's going to be 1/144, otherwise known as, wow, I'm not even going to put that into a percent because it is less than 1. I believe it's like 0.7%, not very high. Okay, I'm going to stop rambling. This is it. I'm going to send it to you guys. You can email me with questions if you want. I'm probably not going to get to them tonight, but what I would recommend is if you do have other questions on this or want to talk about them before the test tomorrow, put little stars, by your numbers that you want to take a look at. Okay. All right. See y'all tomorrow.